Proxima Centauri, the nearest star to our planetary system, has for quite some time been a subject of interest for space experts. This little red dwarf was found in 1915 by Scottish space ace Robert Innes. It is principal to the Alpha Centauri system, which also includes Alpha Centauri A and B. In spite of its proximity, simply 4.24 light-years away, Proxima Centauri remains imperceptible to the unaided eye because of its low brilliance. Anyway, Proxima Centauri holds huge logical importance, particularly as the host star of Proxima b, an exoplanet that orbits within the star's habitable zone. Red dwarf stars like Proxima Centauri and its cousin, Tati, are more unobtrusive, cooler, and far longer-lived than stars like our Sun. Their low glow makes them challenging to notice, yet it also proposes that their habitable zones are much closer to the star. For Proxima Centauri, this means an orbital distance of around 0.05 astronomical units, just a little part of the distance between Earth and the Sun. This proximity exposes Proxima b to huge celestial activity, including ordinary solar flares and elevated levels of radiation, making its environment vastly different from Earth's. The discovery of Proxima b was a tremendous leap forward in exoplanet research. Utilizing the spiral speed method, space specialists recognized subtle wobbles in Proxima Centauri's position caused by the gravitational pull of an orbiting planet. These wobbles allowed researchers to measure the planet's mass and orbital period. In 2016, the European Southern Observatory officially confirmed the presence of Proxima b, marking a significant jump forward in the search for potentially habitable worlds beyond our nearby planetary system. While ground-based observations have provided important insights into Proxima b, they come with significant limitations, like atmospheric distortion and light interference, which hinder the ability of Earth-based telescopes to capture detailed information about the planet's surface or atmosphere. A large portion of the data we have, including its mass, distance from the star, and orbital characteristics, comes from indirect measurements. To uncover further insights into Proxima b's environment and its potential for life, advanced observational instruments like the James Webb Space Telescope, JWST, are crucial. Proxima Centauri and Tati's role as a gateway to understanding exoplanetary systems couldn't be more significant. As the nearest star system to Earth, it offers a unique opportunity to study the conditions vital for life. Proxima b, in particular, presents an intriguing opportunity. A rocky, Earth-sized planet with the potential to hold water and perhaps even life. However, the challenges presented by its harsh climate make it a complex puzzle for scientists. The James Webb Space Telescope isn't simply another tool in the arsenal of space science. It is a revolutionary instrument designed as the replacement for the Hubble Space Telescope. JWST was built to overcome the limitations of its predecessor and push the boundaries of human knowledge. While Hubble has provided significant insights into the universe, including the age of the universe and the discovery of millions of galaxies, its capabilities are limited by its focus on visible and ultraviolet light. JWST, on the other hand, is designed to observe the universe in infrared wavelengths, allowing it to peer through astronomical dust and reveal features hidden from Hubble. One of JWST's key design features is its primary mirror, which spans an impressive 6.5 meters in diameter, over 2 times the size of Hubble's mirror. This larger mirror enables JWST to collect much more light, making it capable of observing even the faintest and most distant objects. The mirror is coated with a thin layer of gold to enhance its infrared reflectivity and is composed of 18 hexagonal segments that work together to form an extremely sensitive observational platform. Another remarkable advancement is JWST's sunshield, which keeps the telescope's instruments at a constant temperature of about -233 degrees Celsius. This ultra-cold environment is essential for detecting faint infrared signals without interference from the telescope's own heat. Unlike Hubble, which orbits Earth, JWST operates from the second Lagrange point, L2, a stable position about 1.5 million kilometers from our planet. This location minimizes interference from Earth's heat and light, allowing JWST to maintain continuous observations. JWST can focus on everything from the earliest galaxies to the atmospheres of exoplanets like Proxima b. Its ability to detect infrared light is particularly important, as it allows scientists to study redshifted objects, those whose light has been stretched to longer wavelengths as the universe expands. JWST's capabilities extend far beyond mere observation. It is designed to answer some of science's most fundamental questions, including the origins of galaxies, the formation of stars, and the conditions that could support life on other planets. With its advanced instruments, including the near-infrared camera, NIRCam, the mid-infrared instrument, MIRI, and the near-infrared spectrograph, NIR-SPEC, JWST is not just a telescope. It is a time machine, a research laboratory, and a testament to human ingenuity. Proxima b has captivated both scientists and the public as a potential second Earth, located within the habitable zone of its star. The planet has the right conditions to support liquid water, a key ingredient for life as we know it. With a mass approximately 1.17 times that of Earth, Proxima b is likely a rocky planet, similar in structure to our own. Its proximity to Earth, just over 4 light-years away, makes it an ideal target for studying the potential for life beyond our solar system. However, Proxima b is far from an ideal twin of Earth. One of its most striking features is that it is tidally locked, meaning one side of the planet is in perpetual daylight, while the other is in eternal darkness. This creates a unique climate, with extreme temperature contrast between the two sides. The area where day meets night, known as the Terminator line, could offer a limited habitable zone with conditions mild enough to support life. The challenges presented by Proxima b's environment are significant. Its host star, Proxima Centauri, is a red dwarf known for its intense solar flares, which can release bursts of X-rays and ultraviolet radiation. These flares could strip away the planet's atmosphere over time, exposing its surface to the harshness of space. If Proxima b has any atmosphere, it likely requires a strong magnetic field to protect it from radiation. Without such protection, the surface climate would be inhospitable to life as we know it. Despite these challenges, researchers remain optimistic about the potential for life on Proxima b. The planet's location within the habitable zone suggests that liquid water could exist either on its surface or in subsurface reservoirs. Life might adapt to the harsh conditions, just as Earth organisms thrive in extreme environments, such as deep-sea hydrothermal vents or high radiation zones. These adaptations could include radiation resistance, subsurface habitats, or novel biochemical processes. The search for life on Proxima b is more than just a scientific endeavor. It is an effort to answer one of humanity's oldest questions. Are we alone in the universe? Proxima b represents an exciting possibility, a rocky, Earth-like world that could possess the conditions necessary for life. As our technology advances, so too does our ability to explore this fascinating planet and uncover its secrets. While Proxima b presents alluring possibilities, its climate is heavily influenced by the nature of its host star, Proxima Centauri. Unlike our Sun, Proxima Centauri is a red dwarf, smaller, cooler, and fundamentally different. Less iridescent, its diminished size and temperature imply that its tenable zone is a lot nearer, maneuvering Proxima b into an orbit only 0.05 galactic units from the star, multiple times nearer than Earth is to the Sun. This closeness makes a novel arrangement of difficulties for the planet and any potential life it could harbor. One critical issue is Proxima Centauri's heavenly movement, especially its extreme and successive sunlight-based flares. These flares are sudden, strong eruptions of energy that release high portions of X-rays and ultraviolet radiation. Such events are undeniably more common and extreme in red dwarf stars than in stars like our Sun. For Proxima b, this means a constant convergence of high-energy particles that could strip away the planet's atmosphere over time. Without a defensive magnetic field like Earth's magnetosphere, any air on Proxima b would be vulnerable to erosion, leaving its surface exposed to brutal radiation. Regardless of whether Proxima b holds a portion of its atmosphere, the radiation from Proxima Centauri presents significant challenges to life. Elevated levels of ultraviolet radiation can break chemical bonds, preventing the development of complex organic molecules. This would severely limit the potential for life to develop or sustain itself on the planet's surface. On Earth, organisms like Deinococcus radiodurans have developed mechanisms to repair DNA damage caused by radiation, suggesting that life on Proxima b could also adapt. However, the level of radiation resistance required would be extreme, possibly requiring entirely new biochemistries. Interestingly, Proxima B's tidally locked nature could offer some protection. While one side of the planet faces constant radiation from Proxima Centauri, the dark side could act as a refuge. Subsurface areas or deep caves could protect potential life forms from the worst of the radiation. Furthermore, if Proxima b has subsurface oceans, they could provide a stable, radiation-free environment where microbial life could thrive, much like the ecosystems around hydrothermal vents on Earth. Despite these challenges, researchers remain optimistic that Proxima b's extreme climate offers a captivating opportunity to study the resilience of life by seeing how organisms could survive or even flourish under such conditions. Scientists can expand their understanding of what makes a planet habitable. Proxima b isn't just a possible home for life. It is a laboratory in the search for life's resilience across the universe. The possibility of life on Proxima b raises more questions than it answers, but it also offers another perspective on the meaning of habitability. The question for life on Proxima b isn't just a scientific mission, but also a philosophical one. It challenges our understanding of what constitutes a habitable environment and broadens our search for life to include planets with extreme conditions. Proxima b's harsh radiation environment and tidal locking force researchers to reconsider the traditional idea of livability, which was largely based on Earth-like conditions. One of the key aspects of studying Proxima b is its potential to reveal new insights into how life could adapt to extreme conditions. If life could indeed survive and thrive in such an extreme environment, it could redefine our expectations for where life may exist in the universe. Understanding these possibilities could help scientists focus on other exoplanets that share similar characteristics with Proxima b, expanding the criteria used to identify potentially habitable worlds. The investigation of Proxima b also fits into the broader context of the search for exoplanets, planets that exist outside our solar system. In the past few decades, the discovery of exoplanets has exploded, with thousands of these distant worlds now recognized. The study of these planets, especially those in their stars' habitable zones, has shifted our perspective on the likelihood of finding life elsewhere. Proxima b, with its proximity and potential for liquid water, is one of the most intriguing candidates. However, it is far from unique. As technology advances, the number of known potentially habitable exoplanets continues to grow. In addition to studying Proxima b, astronomers are focusing on planets around other stars, especially those that share characteristics with our Sun. These Sun-like stars offer habitable zones that might be more stable and conducive to life. However, Proxima b, orbiting a red dwarf star, offers a contrasting case that challenges conventional thinking about habitability. Its study can provide valuable lessons on the resilience of life and how it could exist under more extreme conditions. Proxima Centauri, the star that hosts Proxima b, also offers researchers an exciting opportunity to better understand stellar behavior, especially the differences between stars like our Sun and red dwarfs. Red dwarfs are much more common in the universe than Sun-like stars, and studying these stars can help us understand how different types of stars affect the potential for life on surrounding planets. Proxima Centauri's regular solar flares and the impact of its intense radiation on Proxima b's environment may help researchers determine how different types of stellar activity influence planetary conditions, providing vital clues for the search for life elsewhere. For now, Proxima b remains a mystery. However, technological advances and future space missions may ultimately provide the data needed to answer one of humanity's most significant questions. Is there life beyond Earth? With each new discovery, the possibility of finding life on Proxima b or other exoplanets becomes more plausible, and the implications of such a discovery would be profound. The search for life beyond Earth continues to grow, and Proxima b stands as a beacon for future exploration. The potential for finding extraterrestrial life on this exoplanet has sparked interest not just among cosmologists and space scientists, but also among the general public. Its location in the habitable zone of Proxima Centauri, combined with its Earth-like size and composition, makes it an intriguing candidate for further study. However, the harsh environmental conditions present significant obstacles, prompting researchers to reconsider the traditional boundaries of habitability. One key aspect of Proxima b research involves understanding how life could adapt to extreme circumstances, such as intense radiation and temperature fluctuations. If microbial life, or even more complex life forms, exist or could survive there. They may have unique biological adaptations that allow them to endure these hostile conditions. Investigating extremophiles, organisms on Earth that thrive in extreme conditions, such as those living near hydrothermal vents or in acidic lakes, could provide valuable insights. These organisms rely on unconventional biochemistry to survive, and similar adaptations may be found on Proxima b, suggesting that life elsewhere in the universe may not need to mirror life on Earth to thrive. Another avenue of investigation involves examining the planet's potential magnetic field. A strong magnetic field is crucial for protecting any atmosphere from being stripped away by solar wind and cosmic radiation. If Proxima b has such a magnetic shield, it would significantly improve its chances of maintaining a stable environment suitable for life. Recent advancements in space-based instruments capable of detecting faint magnetic fields could help scientists understand the structure and dynamics of Proxima b's environment, providing more clues about its potential habitability. Looking beyond Proxima b, the study of red dwarfs and their planets opens up broader implications for understanding planetary systems. Red dwarfs are the most common type of star in the Milky Way, and many potentially habitable exoplanets orbit these stars. By understanding the relationship between red dwarfs and their planets, astronomers may be able to refine their methods for identifying habitable planets around other stars, improving the chances of finding life elsewhere in the universe. The mission to understand Proxima b and its environment is not just about one planet, but about the broader context of life in the universe.